Hello to all my viewers. This is Dr. Dhaval Maheta, and today we'll understand how to run neural network in SPSS. A neural network is a computational model inspired by the human's brain structure and functioning. It's a key component of artificial intelligence and machine learning, designed to recognize patterns and make predictions. So this is the architecture of the neural network. It consists of neuron, the green ones, input layer, hidden layers, and the output layer. Let's understand these terminologies. Neurons. Neurons are the fundamental units of a neural network, akin to the neurons in the brain. This one. Each neuron receives input, processes it, and passes it onto the next layer of the neurons. So the processing is being done and then it passes it to the next layer. Layers. Input layer. The first layer where the data is fed into the network. Each neuron in this layer represents an input feature. So here is the input layer. Hidden layers. Intermediate layers between input and output layers. So this one, the hidden layers between input and output. They perform various transformations on the inputs, learning to extract features and patterns. Neural networks can have a multiple hidden layers, making them deep. And hence the term deep learning is used for neural networks. So we can have a multiple hidden layers here. Output layer. The final layer which produces the result or prediction based on the processed data. So this is output layer. Weights and biases. Each connection between neurons has an associated weight with edges as learning progresses. Biases are added to the weighted sum of inputs to help the model fit the data better. We'll understand the concept of weights and biases in the next slide. See, we are having a linear regression equation. Y is equal to alpha plus beta x. Alpha is the intercept, the constant term. Now the same thing, the same equation, if I want to represent in the form of neural network, Y is my output layer, X is the input layer. So the X takes the weight beta and the intercept is represented by the bias, which is alpha. Applications of the neural network, image and video analysis. Start with the image classification. Identifying objects or scenes in images such as recognizing animals, vehicles, or facial expressions. Object detections. Detecting and locating objects within an image used in applications like autonomous driving and surveillance. Natural language processing. Determining the sentiment or emotional tone of text used in social media monitoring and customer feedback analysis. Machine translation. Translating text from one language to another, such as Google Translate. Speech recognition and synthesis. Speech to text, converting the spoken language into written text used in virtual assistants like Siri and voice control applications. Text to speech, generating the spoken language from written text used in assistive technologies and interactive voice response systems. Healthcare and medicines, medical diagnosis, analyzing medical images such as X-rays and MRIs to assist in diagnosing conditions like tumors or fractures. Drug discovery. Predicting the effectiveness of new drugs by analyzing chemical structures and biological data. Finance and economics. Fraud detection. Identifying fraudulent transactions or activities by analyzing patterns and anomalies in the financial data. Stock market predictions. Forecasting stock prices and market trends based on the historical data and patterns. Recommendation systems. Product recommendations. Suggesting products to users based on their past behavior and preferences used by e-commerce platforms like Amazon. Content recommendations. Personalizing content suggestions for users on platforms like Netflix and YouTube. Advantages of neural network. Ability to learn complex patterns. Neural networks can automatically learn and represent complex patterns in a data without requiring manual feature extraction. We don't have to transform the data. This is particularly useful for tasks where the patterns are intricate and not easily captured by the traditional methods such as linear regression and logistic regression. High performance. Neural networks, especially deep learning models, have achieved the state-of-art performance in many areas, such as computer vision and natural language understanding. Feature extraction. Neural networks can automatically extract the relevant features from raw data, reducing the need for manual feature engineering and allowing for the discovery of complex relationships within the data. Nonlinearity. Neural networks can model nonlinear relationships between the inputs and outputs, which is crucial for capturing complex patterns that linear models might miss. Adaptations to different data types. Neural networks can work with various data types, including structured data, unstructured data, such as text, images, and temporal data, that is the time series. Transfer learning. Neural networks trained on one task can be fine-tuned for related tasks using the transfer learning, making them more adaptable and reducing the need for extensive retraining. Now let's try to understand the concept of neural network by this example. The child wants to identify this object. I'm using the word object. Okay. So the child has passed through series of questions. The first question will be, is the object having four legs? So the possibility is chair, table, monkey, and dog. The next question is the object having the skin? Is the object having the skin? So now, these two objects qualify in this round. The next question is, does it bark? Yes. So the object barks. It means that it has been classified that this is the dog. So in the third round of question, monkey did not qualify. Okay. So this is the neural network architecture. Input, the hidden layer, and the output. Now the path which was taken by the child to identify the object. So all the neurons in this path will get activated. So this is the architecture. It consists of input layer, neurons, hidden layer, and the output layer. So this path will get more weightage than others so that the identification can be done properly. So it is known as prediction. So the path, that is the path which is connected with one neuron to another neuron, it's a synapse and it will have some weight. The hidden layer. So how many hidden layers should be there? It depends on the complexity of the problem. Simple problem. For a simpler task such as linear regression or basic classification, a neural network with a single hidden layer is often sufficient. For instance, if the problem involves learning a straightforward relationship between inputs and outputs, a shallow network might perform well. Complex problems. For more complex problems like image recognition, natural language processing, or complex time series forecasting, deeper networks with multiple hidden layers are usually required. These deeper networks can capture hierarchical patterns and complex relationships in the data. Amount of data. Small data sets. With limited data, very deep networks might overfit the data. For small data sets, starting with the fewer hidden layers and increasing the complexity gradually as needed is a good practice. Large data sets. When you have a large amount of data, deeper networks with more hidden layers can be trained effectively without overfitting. Large datasets provides enough information for deeper models to learn complex patterns. Now, how many neurons should be there in the hidden layer? I'm talking about these neurons which are there in the hidden layers. So the formula for this is M is equal to square root of N into L. N is number of input features, L is number of output units or output neurons. For example, if you are having 50 input features and L is 10 output neurons, the estimated number of neurons in the hidden layer would be M is equal to square root of 50 into 10, which is 500. So roughly we get it 22.36. Now let us magnify one node. So let us magnify one neuron. So we are having two analogies. This side is a biological neural network and this is the artificial neural network. Both of them are having dendrites with synaptic weights. Okay, dendrites with synaptic weights. So the neuron, axon, these are the weights W1, W2, W3, W4 and W5. Synaptic weights are the parameters of the neural network that determine the strength of connections between the neurons. They influence how the input data is transformed and propagated through the network layers to produce an output. Each connection between neurons has an associated weight. Okay, so these are the weights which adjust as learning progresses. Biases are added to the weighted sum of inputs to help the model fit the data better. So biases are like intercept. This we have seen earlier. Let's understand this concept, that how the summation is being done. So the node W the node X0 and its weight W0. So this is bias. The intercept X1 WK1, X2 WK2 and XP WKP. So these are input signals. These are synaptic weights and this is summing junction. Okay. Now each node will multiply with its respective synaptic weights after summing up. That is X1 with W1 plus. So the summing up will be done here, plus X2 W2 plus X3 W3 till the last node. Depending upon the value of summing junction, activation function will get activated. This will get activated depending upon what the value is in the summing junction. Let's understand this concept in the next slide. See the inputs, the weights and the summation junction. Now this summation junction is like on off switch. So when the correct value is reached, the threshold value is reached, the neuron will get activated. Okay. So in a neural network, the summation junction or a weighted sum in a neuron, this one is where the inputs to a neuron are combined. All the values, these values are combined. Each input is multiplied by a weight and these weighted inputs are added together along with the bias term, the intercept. The activation function is applied to the output of the summation junction. Here, there will be one activation function which we'll see in the next slide. It determines whether the neurons should be fired or activated based on the combined input. This function introduces non-linearity to the network, allowing it to the model complex patterns. So the activation functions which are normally used are sigmoid and tanh. Okay, these are normally used. Relative linear unit is also sometimes used. Now let's understand this concept. This is the summation junction. This is the activation function. And this is the output. Now this is the image which has to be, which was to be identified. But the network identified the wrong image. Okay, so this is a puppy. Now there is a gap in the identification. This is known as an error. This was targeted, okay, and this was achieved. So there is a gap. This error is back propagated on the synaptic weights. The weights are shuffled again. This process continues till the correct identification of the target is being done. So if there is any error in actual and predicted, error updates the neuron to change the weights for proper identification. This is known as a back propagation. It is process used to train the network. It involves calculating the gradient of the loss function with respect to each weight and bias. So this error is back propagated continuously till the error is minimized. The minimum error is reached. Till that point, it is back propagated. Then adjusting them to minimize the loss. This is done using the optimization algorithm, which is gradient descent. Now let's see the graph of gradient descent. It's very simple. See, this is loss. Loss means the difference in the actual and predicted is loss. The error, it should be minimum. So this algorithm will run till we achieve the global minima. It's just like you are standing on the valley and you throw a ball. The ball will go to the lowest point. This is the global minima. Okay. So this is the initial weight. Then the back propagation starts. Error starts minimizing and we reach to the lowest point. This is global minima where the losses are minimum. Gradient descent is an optimization algorithm used to minimize a function commonly employed in machine learning and neural networks to find the optimal parameters or weight. The goal is to find the minimum of a function, which typically represents the cost or loss functions in machine learning models. Error will be continuously back propagated and loss function will be minimized continuously till we get the global minima. Okay. So once we achieve the global minima, the weights are fixed. So during training, algorithms like gradient descent are used to adjust the synaptic weights. The gradient descent algorithm seeks to find the set of weights that minimizes the loss function. When global minima is achieved in loss functions, all synaptic weights are estimated. Now we are having two types of neural network. One is a multi-layer perceptron and another is a radial basis function. So we start with multi-layer perceptrons. So multi-layer perceptrons are a type of a neural network that consists of multi-layer of neurons, an input layer, one or more hidden layers and an output layer. Structure. Input layer receives the input data. Each neuron in this layer represents a feature of the input data. Hidden layer. Intermediate layers where computations are performed. Each neuron in this layer applies weights, biases, and an activation function to the input data. MLPs can have one or more hidden layers. Output layer produces the final output. The neurons in this layer represents the possible outcomes or predictions. Key features: can work on non-linear functions such as relative linear units, sigmoid, tanh. They are applied to introduce non-linearity into the network, allowing it to learn the complex patterns. Data flows in one direction from input to output without loops. That is a feed-forward mechanism. Back propagation, used for training the network by adjusting the weights and biases to minimize loss functions through gradient descent. Application: classification tasks such as image classification, regression task, that is predicting the continuous values, and the function approximation. Next is radial basis function networks. Don't worry, I will explain both this concept in a very simple layman example. Just let me proceed. Radial basis function networks are a type of a neural network that uses radial basis functions as activation functions. They are typically used for pattern recognition and function approximation. Structure. Input layer. Similar to MLPs, this layer receives the input data. Hidden layer. In RBF networks, the hidden layer neurons apply radial basis functions to the input. Common radial basis functions include the Gaussian function. Each neuron in this layer represents a center of the radial function. Output layer produces the final output. This layer often uses a linear activation function or simple summation to combine the outputs from the hidden layer. Key features. Radial basis function. This function measures the distance from the input to a center or a prototype and apply a non-linear transformation based on this distance. The Gaussian function is commonly used, which depends on a parameter called the spread or variance. Local approximation. RBF networks approximate the function locally around each center, which can be advantageous for certain types of data. Training. The training process usually involves two phases. Clustering, determine the centers and spreads of the radial basis functions, often done using the clustering algorithm like k-means, linear regression. Train the output weights using the methods like least squares regression. Application. Function approximation, pattern recognition, and time series prediction. Now let's understand the concept of multi-layer perceptron and radial basis function in the next slide. Layman example. Concept. Think of an MLP as a complicated recipe that requires multiple stages of preparation. Each stage layer transforms the ingredients data in different ways to make a final dish, which is the output. Stages. In this recipe, you want to bake a cake. The recipe includes multiple stages like mixing flour, eggs, and sugar, then baking, and finally decorating. Each stage adjusts the ingredients to improve the final taste. Learning. If the final dish does not taste right, you adjust the amounts and methods in each step. The recipe is refined based on testing and feedback. This is known as a backward propagation. Radial basis function. Imagine RBF networks as a group of local chefs, each an expert in a specific type of dish. Each chef focuses on perfecting dishes in their specialty. Each chef, that is a RBF center, specializes in specific cuisine or dish. They assess ingredients based on how closely they match their specialty. The example of RBF is you want a dinner with multiple types of cuisine, that is Italian, Mexican, and Chinese. Combining skills. The final meal is a mix of dishes from different chefs based on how well each chef's specialty fits with the available ingredients. You have an Italian chef who specializes in pasta, a Mexican chef who is great with the tacos, and a Chinese chef who excels in stir fry. The final dinner is a blend of their specialties based on how well each dish complements the others. So now let's go in the SPSS data set. Here is the data. So this data set consists of credit rating of the customer, binary, good or bad, age of the customer, income, which is coded either low, 1, or medium, and there is 3 also. So 3 is high. So income, low, medium, high. Credit cards. So we are having code for less than 5 as 1 and 5 or more 2. Just you can see here 1 and 2. Education. So high school and college. Car loans, none or 1 or more than 2. So this is the coding. This coding you can see from here also. Credit rating, if it is 0, bad, 1, good. In income, 1, low, 2, medium, 3, high. Here is a credit card. If it is 1, less than 5, 2, 5 or more. And here education, if it is 1, high school, 2, college. Remember these codes. Please remember these codes. 1 is none or 1, car loans, 2, more than 2. So the target variable is a credit rating. Now we want to study the profile of the customers who are having good credit rating and the bad credit rating. So we'll go and analyze in this neural network, multi-layer perceptron, transfer credit rating in the dependent variable, income level in factors, number of credit cards in factors, education in factors, because they are categorical. Car loans, see here, this they are categories. This one. Now let's talk about age. It is continuous and therefore it has to be transferred into covariates. Now, if you are having many variables which are continuous and they are on different scale, it is necessary to standardize. It is necessary to standardize. At present, we are having only one, so make it none. Now click on partitions. So the data has to be divided into how many parts? So this is 70% is for training, 30% is for testing, nothing in holdout. If you want to change it, you just click here and make it 2 and this as 1. Make sure that the total is 100%, or you can go for 80-20. So this is 80 and this is 2 and 80-20. Okay, so this is also possible. Partitioning can be done on the basis of on basis of some variable also. So here keep it 7, keep it 3, and now go in the architecture. Yeah, so here it should be 0, holdout should be 0. Architecture, minimum number of units in hidden layer 1, minimum number of units, sorry, maximum number of units in the hidden layer 50. Training, keep the things as it is. Output, synaptic weights are to be activated. ROC curve we require. Save predicted value or category, yes. Save predicted pseudo probabilities, yes. Export, nothing is to be done. Options, keep the things as it is. Now click OK. So the network information, training 1745, testing 719. Okay, so this is the neural network model which we got. Parameter estimates, classification, and ROC curve. And this is the area under the curve. Now I have simply copied all this on the slide so that the interpretation is easy. Let's understand this. This is the neural network. So wherever the lines are gray, the synaptic weight is greater than 0. Wherever the lines are blue, the synaptic weights are less than 0. Now just here, this is H1:1. This, the bias is the intercept, the constant term. H1:2, 1:3, 1:4, 1:5, 1:6, and 1:7. Okay. Now see the synaptic weights for income 1, that is code 1, that is low income. Income 2, medium. Income 3, high. Credit card 1, 2. Education 1, 2. Just try to recall that codes. Car loans 1, car loans 2, and these are their weights. Okay. Now let's take one example of one customer. Income is 2. Income is 2 means the category is 2. This one. Credit card 1. Education 1. Car loan 2. And age is 30. So the weighted sum will be bias plus weight of the income. Okay, so this one into income in which category it falls, plus weight of the credit card, this one, into credit cards, plus weight into education, weight education into education, plus weight car loans into car loans. Okay, now let's understand this concept also. See, bias is 0.1 plus 0.275 into 0. This into this 0. Why? Because the customer is in income 2. Okay, so for income 1, the customer is not present in income 1, and therefore we will take 0. So 0.275 into 0 plus 0.378 into 2. So customer is here in this category of income, plus minus 1.108 into 0 because the customer is not present here. This is not his income. Income is in his income is 2. Number of credit cards or the credit card is 1. So minus 0.182 into 1, 0.154 into 0, plus education minus 0.168 into 1 plus minus 0.441 into 0, because this is not his or her education. Education is 1. Okay, so it is 0, right? Plus minus 0.320 into 0, car loan. The car loan is in 2, so he is having more than how many car loans? If we go into the data view, and here is it, variable view, car loan. So it is 2. So more than 2 car loans. So what we will write? 0.268 into 2. Now we will talk about the age. Minus 0.488 into 30. The age of the customer is 30. So we got the value minus 15.110. This is what we were I was trying to explain the summation. This is the summation which we have done, and this is the value which we got. Now we have to see that the node will get activated or not based on this value. So it is minus 15.110. So the sigmoid activation function, this we had discussed earlier. Its formula is sigma x is equal to 1 upon 1 plus e raised to minus z. So here we have to substitute the value of x. X is minus 15.110. So we got this value, minus plus. So given that e raised to 15.110 is a very large number, so we got the value equivalent to 0, right? So just the summation function, and will it get activated or not? So the weighted sum for H1:1 is minus 15.110. Activation function, output sigmoid, using the sigmoid, approximately 0. This means that the output of neuron H1:1 after applying the sigmoid activation function is very close to 0. Okay. The next is the hidden layer 1. This was the input layer, hidden layer 1. Now the inputs of this will go in the output layer. Let's understand this also. Whatever values which we get for H1:1 to H1:7, it will be propagated into the output. So the credit rating 0, that's a bad. Credit rating 1, that's a good. So these are the weights for each node. Now what I'll do, I'll multiply it. Calculated the weighted sum of the hidden layer outputs for credit rating equal to 0. So we'll talk about the rate part. Sum credit is equal to 0. H1:1. Just see here 0.737. H1:2 minus 0.020. 0.575 minus 0.140. 0.242. 0.310. 0.096 plus the constant term, that is the bias, plus minus 0.177. So this was for the credit rating 0. Now the credit rating 1, the good credit rating. Sum credit 1, H1:1 minus 0.712 minus 0.545 minus 0.369, 0.481, 0.319, 0.619 minus 0.507, 0.293. So the probabilities will be calculated on the basis of which neural network model predicts the customer rating good or bad. The classification table. So this is available here. The classification table, here is it. Okay, let's understand this. That we will get the classification table for training as well as testing. So the observed data, the original data, the actual data, bad credit rating and good credit rating. The predicted data by the neural network model, bad, good. Okay, bad credit rating and good credit rating. So 529 are such cases in which the actual data shows that the credit rating was bad and the prediction done by the model is the bad credit rating. So this is correctly classified. 529 cases are correctly classified. Now let's talk about good. So the good credit rating, prediction done by the model, good credit rating. So 858 are such cases which have been correctly classified by the model. So how many cases have been correctly classified? 529 plus 858. So that the figure is 1387 divided by the number of observations in the training data set 1709 into 100%. So so what is the formula for overall accuracy? Number of correct predictions divided by total number of predictions. So in training data set, our accuracy was 81.2%. Now let's go for the testing data set. If you recall, we had divided the data into 70-30. So this is 70% and this is 30%. Now let's talk about this. So here correct classification is 236 plus 382 divided by 755. So 81.9%. So accuracy in testing data set is also quite good. Now let's understand the misclassification in the data. 142. The original data, the actual data, good credit rating 142, but the prediction was done that this is a bad, the customer is having a bad credit rating. So 142 are such cases. Let's see this one. The customer was having bad credit rating, but the prediction done by the model was good credit rating. So 180 such cases are there. So 142 plus 180. These are misclassification in the model, also known as a leakage in the model. This is to be minimized. Similarly, in the testing data set, 62 plus 75 is a misclassification in the model. Next is the ROC curve. So on y-axis, we are having sensitivity. On x-axis, we are having 1 minus specificity. The ideal ROC curve should be as close to the top left corner of the plot as possible. See my cursor, the ideal ROC curve. It should be nearer to y-axis like this and x-axis. This is ideal. If this is there, we say that the classification accuracy is 100%. This corner represents a sensitivity, this one. There is a true positive rate of 1 and a false positive rate of 0, indicating the perfect classification performance. The ideal ROC curve will have an AOC of 1, which indicates a perfect classifier. Now, this is the line of null model. That is, no predictors are included. In such scenario, what is the classification accuracy? Naturally, if the predictors are included, then this curve should be above that. We should get the classification accuracy which is more than the null model, the base model. This means that the model, the ideal ROC curve will have an AOC of 1, which indicates a perfect classifier. This means that the model can distinguish perfectly between the positive and negative classes with no positive or false negatives. So we got an AOC of 0.891, means the model performs quite well with the ability to discriminate between the positive and negative class effectively. The value of 0.891 is close to 1, which signifies that the model has a high capability to correctly classify the instances of both classes, minimizing both false positive and false negatives. Now, let's go in the data set. So, the predicted value of the credit rating according to the MLP model, the probabilities of group 1 and the probabilities of group 2. Okay. Now see, group 2, 0.586 so it is good. This is 0.731, so bad. Now what I'll do, I'll pick up this and bring it here. The actual data, credit rating is bad. The prediction done by the model is good. So this is misclassification. Actual data, credit rating is bad. The prediction done by the model is also bad. So this is correct classification. Let's take this case. The actual data, credit rating of the customer is good. The prediction done by the model is good. So this is also correct classification. Now let's see this. The actual credit rating of the customer is good. The prediction done by the model is bad. So this is misclassification. So good, bad, misclassification, and bad, good is also misclassification. So this was all about how to run neural network in SPSS. For more videos on advanced data analysis using SPSS, kindly subscribe to my channel. You can also refer my playlist in which I uploaded videos on data science, machine learning, and artificial intelligence. Please don't forget to like and share my videos. You can also follow me on different social medias, link given in the description box.